Thank you, Mimi. Yeah, so I don't know if any of you actually heard it. I did do a talk the other couple days on some stuff that we were doing both with our Nav Air folks and with a little bit with our Army folks. And today we're going to do a deep dive into the surrogate pilot, the cost modeling thing. And with that, we had a lot of folks helping us. I'll show you a picture in a minute of a number of folks, but today we're going to actually do a tag team. And I have Mr. Don Allen, who is a specialist at NavAir, and he was so helpful to us throughout the whole effort. It took about a year. And we also have Taylor Fields, and some of you might have actually seen Taylor. He was at the event on Tuesday, and he's going to do a demonstration. So with that, let me first let Don introduce himself and tell you a little bit about himself.
Okay, hello, my name is Don Allen. I am a aerospace engineer by study, and I am an industrial engineer by my actual work. I started for the government in 1990, and so I've been with the government for 31 years. So in typical government fashion, they gave me my 30-year pin this year, so only a year late, so that's good. But 28 of those years have been in the area of cost analysis. So as Mark said, I was kind of the person who provided information to his team and talked about the things that we're facing and problems and use cases that we would need to solve in order to implement MBSE within our cost department. Back to you, Mark.
Thanks, Don. That was great. Yeah, he was fantastic, and we only learned maybe about 20% of everything Don knows, but we're going to tell you what we were able to accomplish here. Okay, so with that, how about you, Taylor? Let's hear a little bit about you.
Yeah, I'm Taylor Fields. I'm a research engineer at Georgia Tech in Aerospace Systems Design Lab. I graduated from Georgia Tech not too long ago and became a research engineer. And I focus on model-based systems engineering for aerospace systems. And so had a wonderful time working on this project. Thanks.
Thanks, Taylor. All right, so I just want to put this disclaimer out there. We're going to talk about some tools, and while our organizations may like them, they're not necessarily endorsing them. The other thing too is that this project's been going on quite a while, all the way back to 2013, and so we've had a lot of research collaborators on our team. So even though you're hearing us talk today, there's been a lot of other people that have contributed to the overall research, including this particular surrogate pilot that we refer to as Skyzer. And so I just want everyone to be aware. So Taylor and the team are over here. So and I'm going to mention a couple of them. So yes, the special thanks to, and always put this back up here with Don, was like I said, it was fantastic. And then also Alexandra Lexi, come on, she also did a lot of work on this cost modeling, and we were able to sort of like share it, look at it. We couldn't directly incorporate it. It still has what's called a distribution D, which is limited to government contractors, and it has some program specific stuff in it. So we had to create another one that was sort of like it, but some of the flavor of it you'll actually see here. Also, we had two students who did a lot of work because this started last summer, and Scott Schmidt actually did his master's thesis and helped us out with the first couple versions of this. And then William Woolstock also graduated from Georgia Tech with his master's degree, and he also helped build a lot of this Geyser for the past couple of years. And then this particular semester, we actually had Dr. Selchuk, and I don't want to destroy his name. I don't know if you know how to say it, Taylor, but I always just call him Selchuk. And then Dr. John Jelski, who's also from Stevens, actually did a little bit of work. Jake Sithapath, as it was a undergraduate student. Sahil actually, I believe, took a job at NavAir. And Gabe Rizzo, who didn't even graduate yet, as undergraduate, he still, maybe I had, is this last semester, he actually did part of the demonstration that Taylor's going to show you. And then Dr. Russell Peak, he's been our, the PI from Georgia Tech, principal investigator for those who don't know what that is. And we actually were just lucky enough to get this, you see at the bottom down there, released as what's called Distribution A, which means that we can talk to you about this publicly. And we have to, again, thank Don, because he was the one who said, you know, everything that's in here is can be actually distributed and shown to the public, which is going to be very valuable because people learn a lot from examples. So we're really happy to have this opportunity to talk to you today. All right, so and in the Navy, they use this term bottom line up front. And so this is like a little bit of like how our agenda would go. And so bottom line is that there's increasing amount of stuff being done with what's called model-based systems engineering. And so if you're not familiar with what that means, normally model-based engineering might be the things that were like the discipline-specific things, which is hydraulics, mechanical, electrical software. And when we move up a level and we have to describe how those things are all related together and linked together, we generally refer to that as model-based systems engineering. It's not a tool, it's more of a paradigm. There's a number of different tools that support that. And it actually, there's a language that's called the systems modeling language, or SysML, and it allows us to describe lots of different kinds of things. And with that, one key thing that came out of cost modeling is the work breakdown structure that is associated with all the work that would need to be done to produce air vehicles or other kind of military kinds of things. And so you're going to see that a little bit today. That's why Don's here to help us understand what's going on with all that. So we did a use case and we took a set of technical specs that was really related to this UAV that we'll talk about, which is called Skyzer. And what we did is that we created a number of stakeholder analysis models, one of those being cost, and we linked it to the actual technical model. And that's really the most important thing and the real main takeaway. And why that's so important is because a lot of times when you get to the cost, it's for the people that are actually running the programs and are making decisions about, you know, what they need to spend. And a lot of times that's come in a number of different kind of documents or this massive spreadsheet instrument that was created over many years, which Don will actually tell you about in a few minutes. But the thing is, the decision makers need to understand all these things and all the impacts and the dependencies. And so when we linked our models to the stakeholder analysis model, they have a better understanding of what things relate to other kinds of things, right? And so when we thought about that, there's this standard, it's called MIL Standard 881E, and we're going to show you that a little bit. But hidden behind those scenes are a lot of these kind of cost estimating relationships and methodologies. And that's the kind of stuff that Don knows, and it may not be obvious from any kind of standard. So that's where he came in so, you know, helpfully for this project. So again, some of the key benefits up front is that we now actually can link the technical models to the cost data. And we're going to talk about a couple of different points in time. So if you're not familiar with traditional types of milestones or baselines, Systems Requirement Review 1 is usually when the government puts out what's called a request for proposal, and SRR2 is really what gets returned, I guess, and then normally after that, and source selection is done, and then they put it on contract. And so we didn't go through the rest of the life cycle, which is sometimes it's called, you know, preliminary design review or critical design review. We never got that far. So therefore there is still work to be done, but I think that at least this is illustrating how it could actually work. And so then by putting it in the model, there's also simulation capabilities in the model. So if you make a few changes to different parameters, it can run the simulation and compute the total ownership cost. And so those are the things that Taylor's going to be able to show you. And so I think that there's going to be a lot of things that can actually happen continuously and iteratively, because we can also have subject matter experts see the views in different ways. So we've actually used some capabilities. One was from the NASA Jet Propulsion Laboratories, JPL, that created a capability called the Open MBE, which allows us to use this DocGen capability to actually generate information from the model and put it in a web browser. But, and Taylor will show you a little bit about that too. And the other one is that we were able to show how we can synchronize data into a spreadsheet. So a subject matter expert could enter a value and then have it synchronized back into the model. So with that, I will proceed on. Unless, Don, is there any other words you might want to say here?
No, I think you did a good job there, Mark. And when I get to my slides, I'll kind of elaborate on some things.
Yeah, so he'll tell you a little bit about these different documents that we actually produced. Okay, so what is Skyzer? It was a search and rescue. We decided to, going back a little bit in time, what happened is that for the first few phases of this systems engineering research, we were doing a global scan, and we went out and talked to like 30 of the best of the best, and that included government, academia, and industry, of course. And they brought their best people out. So this is the most advanced holistic stuff that we're doing. And at that time, Mr. David Cohen, and this was later taken over by Mr. Jaime Guerrero, decided that we needed to go forward and transform, not just evolve from the way that they were doing business. So he created this pilot effort, and we brought in a contractor from Altero is who it was, and they actually became the surrogate contractor for this effort. So we did a search and rescue mission. Dave was always concerned about multi-physics kinds of things, which is, can we do things on the proverbial left side of the system V model, if you're aware of it. And so they brought in some constraints or requirements, such as fly fast and fly far. And when they did the trade space analysis for doing it, they ended up coming up with this Bell Eagle Eye, which is a tilt rotor, which could fly, upwards of 180 knots. And so the interaction that we had with this is with the ship. And so when we first started out, we worked on the airworthiness, which is using the models such as computational fluid dynamics, which actually shows the shape of the actual air vehicle, the airflow, and things of that nature. The next effort was to actually do airworthiness. This is one of the stakeholder models that tries to understand the interaction between the actual air vehicle and the ship. And one of the key concerns is, how do you get a flight clearance? Airworthiness is a set of criteria that is based on another standard that we'll talk about a little bit more, but it's how the actual air vehicle has to come down upon the ship. And so some of the constraints, for example, are it needs to be able to handle a descent of 25 feet per second. So that was that was sort of a difficult one. And then the last one is the cost modeling, which is what we're going to deep dive into today. And one of the things that we did was we just actually focused on the air vehicle characteristics. And so therefore some of the modeling that was done in the early multi-phase modeling is actually being leveraged and used in the cost modeling. All right, another thing I want to talk about here is how do we relate this to everything that we actually have done? And so there's this roadmap that we actually have. It was posted on the SERC, the Systems Engineering Research Center site. And we use this to try to understand how a bunch of different technologies need to come together to support digital engineering in the broader sense. And so the DoD came out with this digital engineering strategy. I think it was signed in late 2018 or around 2018, but they had these strategic goals. One is decision-making across domains of information, across models, many models, the authoritative source of truth. We're going to tell you what that is in a minute here. People use that word. Technical innovations that get integrated into what's going on along the way. A collaboration environment, which is very important to have information access by many of the various stakeholders in various different forms. And then our models also have been used to support workforce development. So we're actually providing those models. We're trying to actually get them, the models themselves. 14 of the 23 total models that were created, we're trying to get released as what's called distribution A again. And so I like to tell a story with this. And so first is that model-based systems engineering in some ways really strengthens traditional systems engineering. And that is that we actually bring together things like structural analysis, like of the air vehicle, or behavioral analysis, like what are the use cases for how it would actually fly or land or other kinds of things, as well as understanding the interfaces in a more rigorous way. And when you actually see, Taylor's going to show you some things that are called for these different kind of properties that we have, how we actually can link those different properties of an air vehicle, such as things that might be related to weight or other kinds of things, to the actual to these actually cost constraints that we're going to show in a few minutes. But so model-based systems engineering is very powerful, and we used a particular tool called from the No Magic Corporation, which actually was acquired, but it was called the Cameo System Modeler, and it uses a language called SysML. And we also used the OpenMBE environment from NASA JPL, which provided a nice collaboration environment. But we also used a methodology that we'll talk about just very simply about how we put the models together to support basically an authoritative source of truth. It's not a single source, and it's because it's a distributed set of models that could also be created and shared with different contractors down the road. And so that's an important methodological way of actually modularizing the models that we are actually creating. We also used the NavSem, which is the NavAir Systems Engineering method, which describes a specific set of ways to actually support process guidelines, which is what we want to do, but also specific artifacts, which is how we're going to do that. And then in a different talk, you could actually see, or the talks that I actually gave the past couple of days, you could go look at that, and how that actually relates to these artifacts that actually are used for digital sign-offs. We also allude to some information about how to use semantic technologies. This is very valuable. So when you're going from using different SysML kind of models to discipline-specific models, we can actually pull that information together in what is called a repository that has like a schema that is based on what's called an ontology, or set of ontologies that actually work together. That helps us have a lot more understanding of the semantics, the true meanings of things, as well as being able to do reasoning about that, which can be done moving forward using artificial intelligence and machine learning, which we also had a different task. And you might have heard Dr. Mark Austin yesterday. He gave a talk about machine learning and AI working together to support a digital twin. And so I've sort of actually just talked about this, but again, let me just reemphasize that for what we're dealing with here, we basically have many different levels of abstraction that we need to model at, but we're also going to include not just requirements anymore. We're going to include the structural analysis, the behavioral analysis, the interfaces, as well as the requirements. And we're going to use the appropriate different kind of modeling methods at different levels of abstraction. And we're going to leverage the new capabilities to allow us to generate different stakeholder-oriented kind of views, because we're not trying to have them necessarily work in the authoring tool. And when we do that, then we'll have the information being actually linked. So as an authoritative source of truth. And when I say linked, it's like it's linked in a way similar to the way that the internet is actually all linked together in some ways. That way we'll be able to actually have visualization through these different kinds of tools and capabilities, things that we can look at the actual, the authoring models themselves, but also different kinds of views, including spreadsheet representations, which again, Taylor's going to give you some demonstrations of those things in a little while. And then with that, if we have all that information pulled together, then it's going to actually help our subject matter experts be able to do things like decision-making with a better understanding of all the kind of dependencies. And we'll actually talk about a couple of those scenarios. And then again, the benefit, again, coming away from this project is that we were able to provide that information to the folks at NavAir, but we hope to be able to use that for workforce development, which is being planned for the future. So with that, so again, what it says that there's various different kinds of information that are in the models. There's the operational kinds of stuff, some of the business models like cost modeling that we're going to talk about. But in general, there's things that are at the model-based systems engineering that are described in terms of MBSE kind of models that are usually referred to as descriptive modeling languages, such as SysML. And so there's the mission models, which describe the systems of systems interactions, like we've talked about. And then normally, the way that NavAir would work is that they would describe the top level part of the Skyzer system. Okay, it's the functional and logical view. What do I mean by that? It's so they would describe the UAV itself and maybe some of the things that it needs to do, which is like to actually have support for landing on a ship. But they may not actually specify, for example, the specific type of landing gear. So it could be an electric landing gear, it could be a hydraulic one, but they're going to leave that decision to be made to a contractor. And so that's what goes on below this line after acquisition. And so what we're going to talk about is actually the cost models up to this point, and then the cost model after that point about these in terms of these descriptive models. And then the other information can be described in terms of these other subsystems like the avionics, the propulsion system. And then that also can get broken into other details that would go down to potentially like the landing gear. And again, so these models up here are usually described maybe as model-based systems engineering models, and they can describe both systems and mission kind of information. And below there, it's the model-based engineering, okay, which is the discipline-specific kinds of information. And so to make that point again, how does this all work from an authoritative source of truth? So given those layers that we actually had, so we have this Skyzer model. So this is not planned, this is not strategic. These are already things that have been done, again, over the past 4 years. So we have a mission model, and we use a particular capability called project uses. It's a way to actually have the system models at lower levels link the actual information that's in the mission model. So the mission model might have things such as, mission level requirements, sometimes also called key performance parameters, or and all different kind of measures of effectiveness that might be described. And so the scenario of like how this is an authoritative source of truth, let's just talk about that landing gear. Suppose that the launch and recovery system needs to actually make some kind of a change, okay? And so therefore that change in that system would actually impact some particular kind of constraint that's actually in the mission model. Because we have an authoritative source of truth, because the Skyzer system model links to the mission model and the contractor model links to the system model, which actually has visibility of the mission model, that information is now visible all the way down to the landing gear level. So a change in one system that might have been in a document in the past is now visible all the way down through this full stack of technical models. All right, so now another thing to add consistency is that we used this NAVSEM systems engineering method, okay, to describe the mission system models, and it actually does have a set of guidelines to describe specific processes that should capture specific kinds of artifacts. So that's how we add consistency. Now, that's always tailorable on any program, but again, it does add consistency to how these different models are made and this methodological pattern for how you would actually modularize the models. So now we're going to get into the stakeholder analysis models, and cost model is actually one of those. So we described a number of instances. So there's different reference models, okay? So in some ways, NAVSEM is a reference model. It is a pattern for how you describe specific things. It's not a specific thing. Same thing with, say, this test model, okay, this is for capability test and evaluation. Same thing for airworthiness. Airworthiness is an instance of the airworthiness model that comes from a standard called MIL Standard 516C, okay? And why it's an instance is because we're going to describe a specific set of criteria that might be described in the superset of all criteria for the specific technical instance that actually the technical information in the full stack of models. So programs don't cover everything. So for example, airworthiness might describe fixed wing models, but also may describe helicopters. Well, some of that might not be applicable to Skyzer if it's a fixed wing kind of a vehicle. So therefore we have a subset of what's necessary. Same thing with cost modeling. And this is what we're going to elaborate on and deep dive on going forward here. So let me go back to my other description again. So with being able to have the cost model, which actually links to the airworthiness model, which links to the test model and also the technical stack, if we had that situation where we wanted to make a change to the launch recovery system and it impacted the mission model, and we might say, oh, wow, that particular change, that might actually mean that we have to have a new kind of airworthiness verification criteria, which means that we need a new kind of a test. But now that's actually linked, the cost models can see all that kind of stuff. So we could do a what if analysis, like could say, well, do we really need to make that change to the launch recovery system? Or, but now we understand the cost impacts of it. All right, well, how do we do that? Okay, well, the way we do it is, and this is going to be the detail part, and this is a lot of the key information, is there's these equations that actually were embedded in a massive spreadsheet, which Don will tell you about. And what we were able to do is we were able to link these equations. They're called parametrics in SysML, the specific language. And they link to the particular value properties that are in these blocks. And Taylor's going to give you some details. So we're just going to spin in on there. But so what we did is we created some surrogate equations, and we would do that so that they are also linked into this model so that we can actually distribute this information, but in reality, the specific cost equations for a program. So once Navigator makes a particular source selection, they actually have equations that are related to the various different contractors from historical purposes. So, and this particular mechanism would also allow the contractors, if they wanted to follow along with this particular approach, to actually link in the model. And so one of the other tasks that we did is we wanted to show another thing that happens with models is that when you formalize the language, you get an additional amount of automation out of it. And so the team, Taylor and Gabe Rizzo, who is, like I said, an undergraduate, they came up with two different approaches. And Taylor's going to talk about how to automatically switch from, say, the surrogate equations to the program equations. So let me stop for a second here. And Don, you want to add anything?
Yeah, I guess I would, yeah, in that scenario, we do a lot of work where if we can interconnect and we trade off methodology. So as Mark was saying early on, we may have, I'll say generic methodologies that are looking across a broad area of contractors who do that type of work. But as we go through the acquisition process, we may down select the different contractors. We will start using that contractor's specific historical data. We will develop unique parametrics for their program and the way their company operates. And then those are the new equations. And kind of each year, as we get more data, as we work through the acquisition process, we will relook at all those CERs. So, a cost model isn't static. A cost model is dynamic, just like a program's dynamic. And so we're constantly updating those things. And the ability to be connected back to the technical models will allow, I think, for greater efficiencies. So it's just really determining how, what type of data we need or artifacts that we need to drive our models, not only at the beginning of an acquisition program, but all the way through its total life cycle to understand those drivers, and then make sure we collect the data, both the technical data, programmatic data, and as well as cost data, in order to continually evolve our methodologies. Back to you, Mark.
Thanks, Don. Yeah, so this pattern is really one that's been flushed out a lot. We brought in a lot of experts, and they agree this is just exactly the right pattern for doing modularization to support the authoritative source of truth. And it also is being applied up here on cyber. Okay, so just to fill that in. All right, so what I'm talking about is there's reference models, and this is a lot of people always ask, what's the ROI of actually going to model-based systems engineering? Well, one is to be able to leverage these different kinds of reference models. And as Don actually just talked about, program models that continually to evolve. And if they evolve the models and do proper model management, that's like configuration control, then the ROI is that when we start a new program, we're not starting from scratch any longer. And so the last kind of reference models, sometimes really referred to as reference architectures, is the generalizations of prior systems. So the generalization of prior UAVs or tilt rotors. But notice, we're not just talking about just the models for the systems, we're also talking about reference models for the missions. So in other words, various different types of search and rescue missions that could actually be applied to different kinds of things, such as trafficking or basically pirating and other things that actually still use the same basic kind of mission, but we're basically beginning to formalize the kind of mission. So from an ROI point of view, there's a lot to be reused, and people may not realize that, but that's a very important thing. And a lot of the contractors, why they should be able to go much faster, is because they've been curating their own models for many years. And so this is the reason why we should expect that we should be able to go faster. And ultimately, that was the whole reason why Dave Cohen wanted to do this to begin with, is it took too long to get these air vehicles out. And so therefore, I believe that there's a lot of evidence, and I believe that we may have captured enough along the way. So anyway, so these models should be available to everybody, hopefully very soon. They're available to anybody that has, that's a government contractor actually right now. So moving forward. All right, so this is Don's chart. So Don, I'll do the build for you, but why don't you talk about this.
Okay. Yeah. So this is just a top level look at the way we kind of approach model building. And I will say when we're building our models, we kind of have a set process. Once we agree that we're going to be building an estimate, that's our step one. Our step two is defining what we call the technical and programmatic baseline. Step three is where we actually begin to develop our estimate. And then once we do, we go through a validation verification type effort, and then we will present our numbers. So what you're seeing on the left are different types of inputs. It's not an all-inclusive list. It's just different type of inputs. So from a cost parameters, we're looking at hours, dollars, labor rates, and we may be using generic labor rates, or we may be using contractor-specific labor rates. Depends where we are in the acquisition process. Technical parameters, if for an aircraft perspective, it's like, what's the weight? Well, there's weight empty, airframe unit weight, structures, the material mix that the aircraft is built from. What type of avionic systems are we going to have on this aircraft? What's the software requirements? What's propulsion requirements? Mark mentioned test. What are the test, types of tests that need to be performed? How long are those tests going to take? What's the number of test points? And then we evaluate risk, like where are the risks in these programs? And programmatically, we want to look at what's the acquisition assumptions. What is the makeup of the contractor team? Is it one prime contractor, multiple subcontractors, or is there a teaming relationship where it's kind of two primes and they share the workload? When work is supposed to begin, when it's supposed to end. So we want to look at the schedule, the plan schedule. And then, we're also being driven by policy. There's certain policies and requirements that we have to comply with, and there's many people that we need to get inputs from. So once we gather that information, we kind of start our modeling process. And we usually, this is kind of what this would be the perfect scenario of how we would want our model set up, is we kind of want everyone to set up a model in a consistent way, kind of give us that contents on what's included in the model, give us what we call a CHEM, which is a cost estimating methodology matrix. So that's where we take the WBS structure. And for every element within the WBS structure, we develop a methodology on how we're going to estimate that structure. That methodology may be used one of the four techniques: analogy, parametric, engineering buildup, or extrapolation of actuals. Those techniques are really driven by where you are in the acquisition phase. Early on in system development, pre-EMD or engineering manufacturing development, we're usually looking at analogy and parametrics. We carry parametrics a lot through EMD, but once we start getting into EMD and we're in there, we start to and we're starting to build and design things, we can start using and define those engineering tasks. We can start using engineering buildup, where we're looking at engineering standards for completing certain tasks and realization factors. And then once we start actually producing the product, we can start looking at the extrapolation of actuals using learning curve, rate curve theory, and regression analysis to kind of predict the future on how much costs are going to be. We usually look at having multiple inputs, like whether they're main inputs, and that's usually by the different options. I know, so say we're evaluating several different configurations of a platform, that's where those type of inputs would be. We kind of have phased inputs, because not only are we concerned with just the overall cost, but we also support, you may have heard the president's budget, the budget that goes up to Congress. Well, we have to phase that money. We have to figure out where the work is going to be accomplished in which fiscal years and how that data is going to be phased. And then I kind of touched on learn and rate curve. kind of analysis. That's the whole idea of, hey, if we do something once, the next time we do it, we've learned from that, so we get better at it. So over time, on the manufacturing floor, the cost of producing something will go down because the human beings are learning as they're producing stuff. Kind of have our calculation sections, and that depends on what you have in calculations is going to depend on the type of weapon system you're designing. If it's an aircraft, you got like airframe, propulsion, avionics. If it's an avionics program, you're just kind of focused in avionics. And then we have the different outputs that we need to, one, support milestone decisions. That's where it goes through a program goes through a review, and when it goes through that review, the decision makers decide whether or not they have met the criteria to pass into the next phase of the acquisition process. And then we also have to kind of, again, show the budgetary effects on where our program may be, what's the budget. So the outputs, we produce budgets to support the Department Navy, the OSD, the Pres budget. We support milestone estimates, but ultimately we also support, like as Mark has highlighted there, the total ownership cost, and that's the complete design, procurement, and operation support and disposal of that weapon system. So think of looking at that weapon system from cradle to grave, from its inception until we dismiss that program, or I'll say they never really go away. We kind of take the assets and we kind of mothball them in case we ever need either repair parts or if we need to bring them back online. Next slide, Mark.
Okay.
Okay, this slide is what I'll say is the total ownership cost as is process. So basically, we use I'll say a documented based engineering process, okay, as opposed to model-based engineering. So documented-based engineering is what's been going on since engineering began. And so what we're really dependent on is we're dependent on the different technical disciplines. They build their documents and they provide their documents to the next guy in the sequence, and then this data eventually flows down to the cost department. And then we take that data and we turn, like I said, we turn all their definitions of that system from the inception of the mission system requirements, which drive the weapon system requirements, which then you look at the technology that can fulfill those weapon system requirements, and that becomes a configuration or a weapon system design that can be defined in terms so we can start producing our cost estimates. So as Mark said, we have, like, I gave them an elaborate spreadsheet that kind of broke down using different aspects of the way we estimate our cost. We mainly are based off of mill standard. We use the WBS structure, mill standard 881. E is the latest. They're in works on F right now. In that appendix he was just highlighting, that's Appendix A. That's for aircraft systems. They have different appendices depending on the types of weapon systems. So I gave them one, an airframe or an aircraft WBS structure that was built off of 881. And it was also built off of kind of the types of documents I will say that we need to support. So I also incorporated what is defined as a P5 sheet. That's an acquisition or procurement sheet that is one of our budgetary documents that we have to submit. And also I used, I'll say, the tribal knowledge that we have here at NavAir.
Oops, we lost your audio, Don. I hope you're still with us. All right.
Yep, I still see Don on, so perhaps Don, if, oh, looks like we're getting him back on.
We lost you, Don. Are you there? All right, well, I will proceed on. So yeah, so Don gave us this massive spreadsheet, and so we use that, and again, it actually mapped to the WBS structure, but it had to be tailored every single time. And so when they would go to a new program, they would take the old one and do a lot of what we used to do, which is called clone and go, and do a save as, and then repopulate it again, and again, evolve the spreadsheet. And what we want to do is to do that in a more rigorous, I would say, approach. Not that this wasn't rigorous. I mean, all the equations are in macros hidden behind the scenes of this massive instrument, and it was very, very large. So let me go on. And so what we did is, and Taylor's going to walk you through this. So this is, we create a cost model, and he built in some very nice navigation kinds of stuff. And he's going to go through the various different parts about, you know, the model, you know, the ConOps, because it also relates to the specific stuff that we had. And then how we did the different information for actually mimicking, in some ways, what was in this model, and being able to show, instead of how you had actually to hand enter these things that are actually would be called the value properties that are actually stored in what's called block definition diagrams. So a block definition diagram is the way to capture structural information in a system model. So it describes the parts, the hierarchy of the parts, but also the different properties of the different blocks, such as, for example, like weight. Okay, and so he's going to go through that later, and then he's also going to talk about and step through this whole model and how it was actually organized, because we did actually clean up all of the models in some ways, made the navigation like this for the final version that was sent over to NavAir. In the early days, we were just making prototypes because we were trying to get through the research as we did a deep dive, but they have been very much cleaned up, and thanks to our Georgia Tech team for doing that. All right, so are you back, Don? Nope, he's not. Okay, so what happened is that, so this MIL standard 81E, so you can see there's various different kinds of information, such as airframe characteristics, the vehicle, you know, there's everything from various types of cost. And so this is a block, okay? And this block basically is composed, it has these different things. That's the little arrow up here, it means this is part of this whole thing. And so what we did is that this represented the work breakdown structure for all things that might need to be put into a cost model. And so we did it for one thing. We looked at something that was related to this Aura is the Future Vertical Lift program that was developed, and Lexi also supported and actually did a number of these kinds of things related to capturing the various different pieces of information for these different things, such as, you know, aircraft systems, air vehicle costs, you know, payload. And with doing all that, we basically were able to show people, one, how you can actually have this, you know, be used as an authoritative source. And so therefore, if you make a particular change to any piece of technical data, because the model actually captures everything that was in that massive spreadsheet, but you'll actually have, again, transparency to understand, like, if we make this change, then it actually affects all these kinds of things. And with the way that we did it, which you'll see in a minute when Taylor does it, we wrote some simulation code that actually does cost roll-ups, okay? So that would allow the government to do even like planning on their own part, which is like they could put in different kinds of things. We laid it out in terms of different kind of cost budgets that might occur in different years, and even talked about use case, which is for a budget change. So in other words, as an example, this year, you know, a lot of additional funds were actually spent, you know, cleaning up the base, and so therefore it might actually, you know, affect what might be able to go to a particular air vehicle. So we talked about different kind of budget scenarios that might actually occur. You back, Don? All right, because I was going to have him talk about this one. All right, so the first thing that we did is we just talked about what's called SRR1, which is there's different kind of cost methodologies and different kind of estimation criterias that can occur whether you're at systems requirement review 1. Again, system requirement review 1 is when there's a review that was done and it's decided internally that they're ready to actually issue the request for proposal, RFP. Okay, looks like that he's coming back in here. All right, are you back, Don? You're back, Don?
Yes, just got back.
Okay,
Sorry.
so all right, I was trying to, I proceeded along without you, Don, but so I was just gonna start to tell them that about this, I'll talk about this, is that we, for our effort here, we were related to the Skyzer system model, which is prior to the issue of RFP, and SRR2, which is when we were being able to look at the cost related to a contractor RFP response. So do you want to continue on with that, Don?
Certainly. As one of the things, like I said, that we wanted to kind of demonstrate within the modeling effort was that, as I said in the beginning, our models are not static. Our models over time evolve. And so what we wanted to demonstrate here is the ability to change as we move through the acquisition process, the ability to change our cost estimating relationships, or CERs. And by doing this, Mark and his team, they were able to demonstrate, okay, I have one set of cost estimating relationships at, say, SRR1, I have a different set at SRR2, and I'm able to switch between the two, and ultimately, if we set up the models correctly and we can determine where we are in the life cycle, we could almost have an automatic switch that says, okay, once you get to this point, once you meet this kind of criteria, we're going to switch to a different methodology that is more representative of that particular platform in that type of in the acquisition process.
Yes, and then continue on. So these are your approaches.
Yeah. So as I mentioned, the methodologies change. Usually, it's typically early on we're doing the analogy and the parametric. And once we get into phase 3, we start to do more engineering buildup. Phase 4 is extrapolation of actuals, or think about that when we're out in production, okay, going down that production line. But as I've also said to the team, that does not mean that if we're in phase 3, all we are using is engineering buildup. In actuality, at every phase in the program, we are probably still using some type of an analogy or some type of a parametric. It's just for certain components of certain pieces of the overall product, we may be using more detailed information. From, like I said, from specific contractors on a specific engineering task or manufacturing task where they have really good history that shows how their companies perform those tasks. So the model becomes, like I said, early on is strictly analogy and parametric, but over time, it takes into account all 4 of those technical, those techniques that are used in cost estimating. And I guess another, yeah, we're good.
Okay, yeah, so what was done is that the OR model, which was done again by Lexi with guidance, is that they actually described all of the different kinds of things, or not all, but it was an evolving thing. You can see this was version 58 that we have here, but we're going to actually do a deep dive into the airframe characteristics over here. But they have various different kinds of things that they actually captured. You can see they're related to this key, so I'm not going to go into that. So we ended up just deep diving, and that's what we always did on all these Skyzer projects. So do not think that the Skyzer project is it's a complete air vehicle. It's really a bunch of deep dives, but it actually is a deep dive that actually shows you how to do each different kind of thing that we're doing. So this, remember I talked about blocks, and they actually have these block, value properties, okay, which can actually be numbers such as the empty weight, the structural weight, these kinds of things. So we looked at the airplane characteristics, and we focused right on here, but you could actually look at propulsion or avionics and various kinds of things. And that's the kind of information that was calculated in the spreadsheet. And then we can actually map those to other kinds of air vehicle kind of characteristics. And this is, what we're going to step you through in a minute with Taylor in his demonstration. So again, what we would do is we would actually get these estimates from the way that the people that are the subject matter experts at NAVAIR would think would be reasonable kinds of things, and they would be able to be used to estimate the cost of what they expected the contractor to respond with in their RFP response. And so after the contractor would do their analysis, they might actually come up with different kind of values that are, again, refined in the cost estimation. So you want to say anything additionally, Don?
No, I think we have it covered. I think.
Okay. So what was done in the Aura model, they actually had these. This is called a parametric. Okay, so I tried to do a blow up. It's a little fuzzy here, but it turns out that you take those value properties and you and have constraints, and those constraints basically feed forward such that they can actually get various different types of cost outputs. Okay, and so these equations, we use surrogate equations. We use some prior reports that may have come from, say, like the RAM company or the RAM Corporation. And so they're surrogates, but we are also going to show you two different approaches. Taylor's going to show you on how we can substitute out generic surrogate set of cost equations with specific ones, because they actually have real ones that they would actually use, but when we want to try to provide this model to other people to show them how it actually works, we're going to provide it with you with the surrogate equations.
Yeah, that's important to note. All the equations and stuff that are used in these models that are being made available, they're published, CERs in publicly available studies. So in no way is it program specific to any company, to any program. It's usually a collection of data that, like I said, when they pull this and run pooled regressions and do, I'll say, generic CERs.
So what we would do is that we take the information from the model. So if anybody's have seen an authoring tool, and we connect it to the cost equations, and there's a capability inside of a lot of these MBSE tools to actually take those specific values. So we talk about specific instance values that you saw there, and they can run these parametric equations and compute these numbers. And so therefore, this can happen immediately. I mean, the computation might take a number of seconds, but it can actually give you, whatever the labor time, the actual, total cost of ownership, development cost. And so there's various types of outputs that can be computed from the instances of the real input, the real technical data, continuously. Any additional thing you want to say, Don?
No, I think we're good. I think
okay. And so
move forward.
And so there, when we go to SRR2, clearly the information, such as the real vehicle information, such as what kind of landing gear we're going to have, what kind of propulsion we're going to have, and those kinds of things, all begin to use this what's called a roll-up pattern, where we take the lowest level piece of information and we roll it up to going up through the levels of systems, so that we get the total kind of cost. And there's a roll-up pattern that Taylor's going to show you, and how we can actually put that information in is like, you don't necessarily have to put that in directly into the model. We're going to show you how a subject matter expert could enter that information either through like a web tool that actually does connect to the model, and also how it could be done, say, with a spreadsheet that can synchronize to the model. But the why you want it to go into the model is because the model has what's called model management kind of capabilities, and it does systematic configuration control right down to the individual value property if you ever need it. So any other comment on this one, Don?
Yeah, I mean, I think that's important. I mean, we, again, as we evolve, and this the whole idea of being able to roll up as the models evolve, we have better and better data. So we usually, go to a lower level of the work breakdown structure, in which is a product-oriented family tree. So early on, we may just be estimating at the airframe level, but later we may have more details now that we have a specific contractor, and we may start breaking that down into, say, forward fuselage, center fuselage, and the aft fuselage, and break out our wings and our empennages. Same thing with our propulsion. We will start looking at, as opposed to generic engines, we will have specific engines designs and software. So you want a model that can I'll say, kind of like an accordion, that can extend out as we get better and better information.
So, so this is just a little bit of a blow up that actually talks, you can begin to see the different equations. So you can factor in development, operations, and production kind of things to get basically your total ownership cost. Same different kinds of things that can go on here, which was basically the engineering, build, cost, again, bringing various different kinds of things in. And we did some other kinds of things looking at it from a multi-phased year point of view. And one of those kinds of things that Don talked about is a 60-40 beta curve. Don, you want to talk a little bit about this?
Yeah, as I said, our job is not only to say what the total cost is going to be, but we have to develop our budgets. So this is one technique early on that is used. It's called a beta curve. 60-40, meaning here that 60% of your costs are kind of expensed or used up within 40% of the time. So that's just kind of defining that shape of how the data is being, or the money is being spent, or the work is being performed. Now there's different beta curves for different types of tasking. And we kind of look at that. If we go to a lower level, we can look at that. 60-40 is kind of the rule of thumb that most major development programs and the Department of Defense kind of follows. So that's why we kind of had that priced out. But there's other phasing techniques too that we look at. But this was to demonstrate the ability of SysML to support a phasing technique within the model. Over.
And then here's a particular example. And so when we did this, we were just looking at different years, as John said, and we would look at the different costs that actually occurs for these different kinds of things over different kinds of years. And this is actually one of the tables that was actually calculated within the model. All right, and now we're going to talk, I'm just going to briefly highlight a few of the scenarios that you're going to see that Taylor is going to execute. The first one, which was a budget adjustment, and obviously in the COVID situation, that was an interesting one to do. So we basically came up with a way to do transactional kinds of things. And so this would actually say that, and there's an important point here, which is, so there's this budget financial manager, and that person he's more from, I guess, from Don's organization, and he would. All right, Don, go ahead.
Well, actually, yeah, the budget financial manager, they're actually within the program office, and I mean, their job is to actually, I'll say, put the finishing touches on a lot of the budget documents that go up to support the Department of the Navy, and then OSD, and ultimately the president's budgets. But there are times, due to circumstances beyond our control, COVID is kind of something that was beyond our control, that may affect the way a program is going to be completing their work or expending their money. And so sometimes to balance the budget, we have to make a transaction of moving money from, say, one fiscal year into another fiscal year, or from one activity to another activity. The BFM is usually the person who gets that type of tasking. They work with the cost team to say, okay, if I need to shift this work from one fiscal year into another fiscal year, what is that going to do to my budget, and how do we have to kind of rearrange or move money around? And there's a whole process of how you move money around in the government. But we're part of the thing. So they go back to us. We kind of give them the perspective, okay, this is what's going to happen. This is what the model says. And then they institute that change.
Okay, and so
Over.
so Taylor's going to show you a couple of different mechanisms, I believe, on this. But what was also important in this scenario is that we wanted to emphasize the fact that while the BFM might have made the request, the actual committing up to the actual model might actually be a different individual with a different set of authentication rights. So for example, so the BFM might have been able to use, say, our view editor, which is this thing that's actually related to our DocGen. And actually, if he has permissions, he can actually edit and change a particular value in this web-based view. Taylor's going to show you how that can also be done with Excel. And so therefore, this particular scenario actually changes the value in the actual web view. And you can see there's a particular element history here that's going on in what was called the model management system, but that's not necessarily the actual repository. And so therefore, once that information gets synchronized over back into your authoring client, then you can actually see that the particular value that got changed. And now a different specific cost modeling individual that actually has access to this, which is a different set of access control that might actually be read, write, can actually make some changes, either basically update it, ignore it, or say that I'm not going to accept it. I'm going to actually put the other value back into the actual, what the user views can actually be. So having the appropriate access control was a very important point for some of the leadership that Don works with. Did you want to say anything additionally about that, Don?
No.
Okay.
I think that's good.
Okay, and so then the other thing that they also maybe didn't realize was that, okay, so this is what's called Teamwork Cloud. This turns out to be the repository that manages ever-changing versions. And so the actual thing is that even if someone made a commitment, and so therefore there was basically a person that had appropriate access, if that particular commit was actually viewed as is not what they wanted, they can actually do a rollback, okay, to prior versions. And so therefore, no harm, no foul. Okay. And so this is just what's called the P5 sheet. You're going to actually see, Taylor's going to bring this up, but it also is a nice thing to actually show how you can synchronize. You can see spreadsheets and actually see the particular values that got changed. And so because Taylor's going to go through that, I'm not going to talk too much about that right now. And this is the lead into some of those kinds of things that he's going to do. He's going to talk to you about the models, the organization, how you can navigate, and then he's going to go through a few scenarios such as the cost roll-up, mechanisms for synchronization using spreadsheets, and automated cost equation substitution. So with that, are you ready, Taylor?
I am. Yes.
Okay. So let's see here. Stop sharing. Okay, you should be able to go, Taylor.
All right. Let's see. Let me know when you can see my screen.
I can see your screen.
All right. Hello, everyone. I'm Taylor Fields, and I'll begin giving the walkthrough and demonstration of the Skyzer cost model here. And so we've constructed an organization system over here in the containment tree. So this over here on the left is called the containment tree. And we constructed this organization. And so one important thing to remember while you're looking at a software like this, this is Magic Draw. So this is a SysML authoring tool. There are others. There are Papyrus and a few others that can author SysML as well. And so what's important to remember about this is that while the diagrams show what you want to show, the containment tree is the model. It shows the accurate representation of everything that is contained within the model. And so the diagrams are used to illustrate those things that are contained within the model. And so that's why SysML, systems modeling language, is depicted as a graphical modeling, like a graphical representation of the programming that you're doing. So here, over here in the containment tree, we have this navigation to help us get through the model, to see what's in here, to see all of the things. And so you can see we have them numbered 0 through 6, and then some of the other things, lower numbers or higher numbers, however you look at it. And so here we have the overview. And so this diagram is showing the overview of the cost model. So if you're unfamiliar with this and you're wanting to get familiar with this, would be a great place to start. So we will start here with the overview. And so here we have the rendering of the Skyzer UAV and the image of the work breakdown structure spreadsheet of the cost analysis. And so we're basically illustrating that the goal of this is to replicate the capability within the spreadsheet, except that is in a document-based form. We want to represent it in a model-based form, and then have the capability to where it can be it can evolve over time as well. And so here we have the introduction column in the beginning, and this column gives an explanation of the Skyzer UAV description, as well as some design requirements,
recording in progress,
and performance requirements, and so on. And so here, the next column, then we have, also we have the Skyzer ConOps. And so just showing what the mission is, what we're trying to do here with the Skyzer system, and represented in OV1 there. And so here in this next column, we have the cost model. It's the core of the cost model. And so this is where we have value properties, cost roll-up patterns, parametric diagrams, instances, and a lot of the things that Mark and Don were talking about exist here in the core part of the model, and they serve to make up the cost analysis. And so you'll see here that we have two cost analysis setups. We have SRR1 and we have SRR2. And so SRR1 uses the Skyzer government model and cost estimating equations from aircraft airframe cost estimating relations document, also known as RAND. And so this setup calculates metrics such as program cost, engineering hours, development support costs, material costs, flight test costs, and they do this from inputs such as max takeoff weight, operating empty weight, max airspeed, and so on. And so these inputs come in from the government model and are utilized in the cost model. And so I'll talk a little bit more about that in a little bit as far as project usages go and what that is and what that looks like. And so they'll use that. And then we have SRR2, which uses the Skyzer contractor model. And so this setup uses a recursive cost roll-up pattern, which is a different methodology. And it uses this roll-up pattern from the contractor model. And the main outputs from this setup are metrics such as program costs, vehicle costs, subsystem costs, and so on. So these are calculated from inputs like tooling rates and hours, labor rates and hours, engineering rates and hours, and then the cost of individual components. And so from there, we developed the parametrics that convert the total cost and time estimates into yearly program phases based on the phasing schedule that was mentioned earlier. And so our model assumes a 10-year program and then follows the 60-40 beta curve phasing schedule. And this will take the outputs from the cost model as inputs and output fiscal year total ownership cost, development cost, EMD, design, and build as well. And so the third column over here in this overview diagram shows use case examples of how we've applied the cost model. And so using the cost model, we were able to construct important documents and views and tables that are used by cost analysts or managers, supervisors to make decisions about programs' budgets. And so after walking through some of the model quickly here in a minute, then we will kind of shift the area of focus to these demonstrations, demonstrating the sync with Excel, the open MBSE, with the budget adjustment example, and so on that Mark had mentioned. And so now we'll briefly step through the model using our custom built navigation buttons. And so we hit this next, it'll take us to the home page. And so we have an overview page and a home page. So this home page is where you want to go when you're sifting through the model and you get lost along the way. And so you want to go back to the home page to see a summary of everything again. So this is meant to reflect what's over here in the containment tree. But here again, the diagram shows what we want to show. The containment tree has all of the information. And so, so here we want to be able to step through using these navigation buttons and show you everything that we want to show as far as what's in this cost model. So if you wanted to go to any of these packages, all you'd have to do is double click and it'd take you there. So we'll just go with the start button down here. And so we'll start off showing the Excel spreadsheet that we intend to capture in the cost models. And so we have this reference button down here at the bottom. And once we click on this, this takes us into the structural hierarchy of the tilt rotor UAV. And I know this is kind of hard to see, so I'll zoom in a little bit here. And so we have at the beginning, we have this tilt rotor UAV, has these properties and so on. And then all of these relationships represent a directed composition is the technical name, but it means that these things are a part of the tilt rotor UAV. And so you just have these different subsystems or assemblies. And then even further down, they can be decomposed. And so that's what Mark meant when he said that block definition diagrams are meant to show the structural representation or the structural hierarchy of a system. And so this is what this is, a block definition diagram showing the breakdown of the tilt rotor UAV, and then also showing the details that belong to those particular components. And so I want to stop right there and talk about how these project usages come into play. So this particular diagram is not in the cost model. And so while that kind of sounds confusing because it's pictured here, it's not technically in the cost model, but it is in the Skyzer system model or the contractor system model, excuse me. And so this contractor system model that you see here in the containment tree is actually being what's called project used into the cost model. And so we have this overarching package here called project usages. And so what that means is we can have a lot of separate models, but these models can be connected to one another by using the project usages. And so when Mark was talking about the full stack of models, we had the mission model, system model, contractor model, all of these things, and then all airworthiness and cost model utilizing these different things, so we can utilize the information from the system model in the cost model. And so when we open up this package, we can kind of look through. We have airworthiness. There's all of these other types of models. We got mission model. All of these packages that you see, these are almost pre-brought in when you construct a SysML project. They want to bring in these SysML constraints, things that are profiles that are specific to the SysML language, because SysML is based on UML, but there's a few differences. But anyway, so here you can see that we have the Skyzer system evaluation model, we have the mission model, contractor model, and all of these have their own containment trees, if you will, and they have all of the information relevant to, say, mission or the system, airworthiness, just to name the few. And so we can use this information. And so if I click on this diagram here and I search for it, it'll take us to this Geyser contractor system model within this project usages and show us, oh, well, all of these properties, all of these blocks are found in the contractor model, and not necessarily in the cost model, but the cost model can use these properties and elements. And so just wanted to illustrate what that looks like a little bit. Project usages. You can also go to options here, project usages, and see their Skyzer system model there. We're bringing that project in. And because the Skyzer system model is connected to the mission model, then that by default, it brings in the mission model as well. And so, and there it is right there. And so you can see also here that we have versions. And so Mark had mentioned we can roll back to different versions if we need to through Teamwork Cloud capability. And so if your project is dependent, say the cost model is dependent on version 60 of the Skyzer mission model, but you want to continue developing the mission model in ways that, you know, maybe the cost model doesn't need or doesn't necessarily have to have a requirement for. You can keep with the version 60, or you can update that version by going here, updating the use project, and you can maintain that it's always the most updated version, or you can use these versions, these later versions as places where you can do development until it's ready. And then in the meantime, you can use the latest version that is ready while you're developing your other models. And so in this way, you can kind of have this version control, not only with the specific model that you're in, but also the project use models that those models are using. So hopefully that wasn't too confusing and was clear for you all. So coming back here, and also just a little bit more about Teamwork Cloud here. All of the models can be found in the open server project here. And so you see how many models we have here for the Surrogate pilot project. And so there's so many here. And then even these projects themselves can have, so this is the cost model, they can have branches. And so if I open this up, we have the trunk branch, the 2021 branch, and then these, 6 branches of the Skyzer cost model. And so you can see how this can all be managed with this Teamwork Cloud capability, keeping up with the branches, the versions, and then merging and all of this stuff, and then keeping track of all of these models. Teamwork Cloud makes it easy to do that. And then also you can see commit histories here. So you can, if you're a manager, you can see what your team is doing. We've got the comments over here to see exactly the types of updates we're doing, and if you wanted to go back to a particular version of the Skyzer cost model, we could click right there and then click set as latest, and that'll bring us back to a version. So if something gets broken in version 246, we can roll back to version 242 and say, okay, let's try to redo something there to make sure that we're not breaking anything. So that's a very useful capability. I found that useful when I accidentally broke some things along the way in the development. And so that's just a little bit about Teamwork Cloud there. So now we'll continue walking through the model here. So next we have the Skyzer cost model block. And so that's this guy here. And it contains constraints, and these constraints are the cost estimating equations and their inputs and outputs. And I'll show that on the next diagram. But it also has these value properties. And so these value properties are specific to this particular block. And so we have regression slope, regression offset as inputs, and then these other value properties can, they may be outputs. And so these are just properties that may have a particular specification towards this block. And so if you click on it, you can define the type of these things. So it can be a real, it can be string, it can be value, an integer, or you can create your custom ones, which we have this, dollar or hour. Some of these are custom, some of these are already built in. And so we have these, you can give these value properties types, you can give them default values, and so on. And I'll continue to explain the value properties as we walk through here so that you can get a better picture. And so we have the Skyzer cost model that's related to the Skyzer UAV system. And so we have the block here that it is in the cost model, but we have the Skyzer UAV system here that's not in the cost model, but you see they've got this relationship between them to say that this system is a part of the cost model, and we're going to utilize the things here in this system. And so these are the disciplines that are specific to the UAV system. And so here again, if I search for this in the containment tree, you'll see that it is part of the system model, the Skyzer system model that's been project used in, and it has its own value properties. And so if I zoom in a little bit here, you'll be able to see the value properties all the way down. And so these four that I've kind of brought out to illustrate, these four pink boxes or red boxes, they represent a graphical representation of what a value property looks like. And so if you look at OEW, it's right here. It's the same thing, or number of test aircraft, number of test aircraft. But I brought these out specifically because we use these particular value properties in the next diagram in the parametrics. And so that's what I'll show now, where we have the cost estimating equations represented in a parametric diagram. And so that's what this is, parametric diagram. We have the constraints. And so if all of these blue boxes are represented back on this diagram here as these constraints. And so all of these constraints on the Skyzer cost model are represented here in the blue boxes. And these yellow boxes are their inputs and outputs. And so if I zoom in on program cost estimate here, we have that program cost equals this equation has these inputs, EW and speed, which is empty weight and speed. And that's what these guys are. And here's the output program cost in dollars. And so that's another value property that's associated with the Skyzer cost model block. And so if I just really quickly go back here, we can look at program cost. That's the value property. That's the same thing, just represented in different ways. Same value property there. And so whatever value comes out of here will be owned by the Skyzer cost model block here. And that's important when we get into creating instances and explaining the data over many fiscal years. And so remember the four value properties that I illustrated from the Skyzer UAV system block on this diagram. See these max speed, number of tests of aircraft, operating empty weight, and then takeoff gross weight. These are the same value properties here represented on this parametric diagram. And so it's owned by the Skyzer UAV system, but can be used in the parametrics of the cost model. And so we have our inputs, regression offset and regression slope, that come into empty weight estimate, and the operating empty weight that comes out of there feeds into the value property of the Skyzer UAV system. And then that's used to calculate many of these other estimating relationships. And so in that way, we have begun to use the Skyzer system model data in the Skyzer cost model. So hopefully you can see that that's clear. We're taking the value properties from the system model and using it here in the cost model. And this is just one of the representations of the benefits of a model-based representation of your system, whether it be the product breakdown, whether it be a behavior representation, or even a design process representation, or even here a cost model representation. You can have these integrated models that when there's a change in one can be propagated to another, keeping everything like Mark was talking about, the authoritative source of truth. All right, and so we'll continue on here, getting into the SRR1 cost methodology. So we'll go to our next block here. And so you can see our Skyzer cost model block, which is the same that I showed you in the previous diagram. And this is where we're mapping these inputs to these outputs. and these value properties come from, we're mapping these to the separate value properties. So we're setting equivalent to Skyzer cost model value properties with the SRR1 cost input value properties. Okay, so this is the Skyzer cost model block, and these are the SRR1 value properties. And so we're mapping these inputs with these outputs, making sure that the SRR1 cost inputs are related to the Skyzer cost model value properties. And then down here, we have our phasing parametrics where we have the program length comes in. We have all of these representative equations, and then we have these outputs that are used in the SRR1 cost methodology. And so this is where, so we have down here, we define the cost inputs. So we have the summary of these inputs. And so if I go here, we can see the inputs, engineering time, labor time, tool time, so forth, that go into the SRR1 cost methodology. And then if we go to this next block here, we can see what's called an instance. So we created an instance of the SRR1 cost of this fiscal year cost block. And this is just as like a snapshot of one of those blocks. And so the block is, if you're familiar with programming or software engineering or anything like that, a block is almost equivalent to a class in say Python or something like that. And then you can create an instance of that class, which is what you see here in this yellow box. It just creates a snapshot, and you can create many instances, which we've done here in this table. And each instance of the block represents a fiscal year within that 10-year period. And so then we have our total ownership cost, which is calculated from those SRR1 cost inputs, development cost, EMD design, build, and so on. So you can see we have now a nice summary table of these instances from fiscal year 2020 down through 2029. And now we'll get into the SRR2 cost methodology. And so now we're bringing in the tilt rotor. So I showed you the tilt rotor UAV in the beginning, and how that's project used in. And so here's one of its value properties being used in the SRR2 cost analysis. And then also using the SRR2 labor cost inputs here and getting a procurement cost coming out of there. And so similarly to SRR1, we have the inputs to SRR2. Here's the production phasing, the development phasing numbers here, the engineering time, labor time, material costs, and so on. And then we also have this cost roll-up pattern that we have utilized for the SRR2 cost methodology. Basically doing what it says here, that the total will equal the parent plus the sum of the child. And so, just like any system, you have the structural hierarchy breakdown. And so if you're looking at a car has wheels, and those wheels have tires and so on. And so there's this breakdown. And so if the sum of the tires, and they have a quantity of 4, so you can take the cost of one tire, multiply it by 4, and there's the cost of all the tires. And then if you take the cost of all the tires and you add it to the total vehicle cost, then you are summing up all the way to the parent where you have a total vehicle cost. And so in that same way, we're utilizing this cost roll-up pattern to get a breakdown of the cost of the Skyzer UAV system. And so that's what's shown here on this table, is that you can see SRR2 cost analysis instance. And because that all of these components from the Skyzer RFP or the Skyzer system is a part of the SRR2 cost model, then we are able to see this structural hierarchy breakdown also within our cost representation. And so you have the cost here, you have the total cost, and these things add up. So if you were to add up wing, tail, and fuselage, and then also the cost of the airframe, you'd get a total cost for the airframe of 50. So that's 20 plus 10 plus 10 plus 10, and that makes 50. And so these numbers are just representative. And then you can also sum it up, and then you can see all of the times for engineering, manufacturing, and so forth, and then all the way down to our procurement cost, our total cost for the SRR2 cost analysis there. And so that shows the cost rollup pattern as well as this breakdown here. And so you're able to see that in a nice summarized table. And so just like in our SRR1, we can show the breakdown for each fiscal year for SRR2. And so we have the total ownership cost, the same things that we showed in SRR1, but we also have this production and development stuff and just showing these instances for each of the fiscal years for SRR2. Okay, and so so now we'll get into our applications, the Skyzer cost model applications. And so this we have budget adjustments, open MBSE that we keep mentioning, and that's a open model-based engineering environment used to sync between a server that's online and your model, and then create views and documents, model-based documents that are interactive and almost alive, so to speak, so that when there's ever a change in the model, it'll be reflected in those documents without having to create a brand new document each time there's a change, which is makes it easier to do that. And so we also have sprawl chart and P sheets and all of these things, and we'll walk through what that looks like. And so the first thing we'll show here is the how we can construct a sprawl chart from the cost model. And so if we go here to, actually, I can scroll over here in the containment tree, show you what that looks like for the sprawl chart. So we have the sprawl charts made up of all of these things: procurement, quantities, RDT&E, system O&M. We have your totals and program totals and all of this stuff. And so just to show what this looks like, we are going with the RDT&E representation here. And so here we show the block for the RDT&E and the value properties that are relevant to the sprawl chart representation. So required cost, prior, current, delta prior, delta required. And then I can show you what those look like on the parametric diagram. And so now we'll go into the mathematical representation of the RDT&E section. And so that's what this looks like. And so we have this development cost coming in from our cost model, and that comes into this to look at the required cost, to calculate required cost. We also have this budget adjustment value property. So if there's ever a change in the budget adjustment, it can be reflected all the way down to the sprawl chart. And this shows the RDT&E portion of that. So you get a required cost out, and then that can be used to calculate your current cost minus your required cost to get you your delta required in this value property. And in the same way, you can do your current minus prior to get your delta prior cost. And so this is the mathematical representation of what that looks like. And so now we can show the calculations here. And so we can simulate the block using Cameo Simulation Toolkit, and then save the instances of the values and generate a table that looks like this for each fiscal year. And so this process is done for each portion of the sprawl chart, such as procurement, system O&M, quantities, and so on. And these instance tables can be displayed to a web browser to be viewed by the necessary people without having to dig through SysML. And so if you're a person that doesn't want to have to dig through this containment tree to find this table, then Open MBSE would be useful for you, because we can take this table and construct it in a document in a web browser where it's easy to use. And so I will demonstrate further capability with this in our next demonstration, which brings us to the budget adjustment. And so this document this diagram just shows what it looks like to construct a document for that web-based interface. And I'll show a little bit more about that later. So I'll demonstrate the budget adjustment use case application now. To set the stage, I constructed this use case diagram, which depicts the steps to be taken in this scenario, which Mark and Don have walked over, and then also who's responsible for each step. And so these actors are who's responsible for each of these use cases here. And so the budget finance manager, the BFM, makes the request, cost team lead accept request, and then cost modeler and the BFM can update the web interface with the budget adjustment. And then the cost modeler will update the cost model with the budget adjustment that comes from the web interface, and then reevaluate, run the simulations again with those adjustments, and then get the new values out, submit those new values back to the web interface, and then the BFM can observe the impacts of those changes directly on the interface. And so that's the process that we'll walk through. To begin here, we've created a block that represents the budget adjustment. And so this block has properties that are important to capture when making an adjustment, such as value, the reason for adjustment, when, who, from what year, to what year, and so on. And we can create instances of this block for each budget adjustment and list them in an instance table to make it look almost like a bank transaction table. And so that's what this looks like here. And so this table, much like the sprawl chart from before, can be published to the web interface, which is called View Editor. And so this can be seen and interacted with by the BFM. And this is constructed using view diagrams and viewpoint methods like shown in this diagram here. And so we have the view, which is the diagram there. And then this is the budget adjustment instances, which is what you saw in this table here. And this is the viewpoint method. And this is a complicated diagram that basically just takes in the information from this diagram here and manipulates it to construct it in table form on the web interface. And so we define the document in the views. We define the document here, and then this is almost like a chapter within this document. And so you can construct it in that way. So now I can, let's see, on the sprawl chart, it can be seen what happens to the budget adjustment for a particular instance. And so in fiscal year, let me switch over here and just show you what the view editor looks like first. So we have this Skyzer cost model, we have sprawl, Skyzer cost model document, which is a summary of everything that I've already gone over. And then we have sprawl P sheets, budget adjustments, and so on. And so I showed you the sprawl chart for the RDT and E table. And so we can click on this document. See, this is Google Chrome right here, just opened up into a web browser. Click on RDT and E, and we can see this table here that comes directly from the model. And it's a representation exactly what's in the model. And so if anything needed to be changed here, somebody could go to edit here and click on one of these values, edit the element, and you can change the value if need be. And so it's important to see on this table that we have this budget adjustment column, and I have, pandemic adjustment 1 as example, pandemic adjustment 2 here. And so if we switch back over to the budget adjustment here, we have the budget adjustment tables that we can show, and it's based on the instances from the cost model. And here I can make a budget adjustment, assuming the cost team lead has approved the request to make an adjustment. And so notice the columns of this table correspond to the value properties owned by the budget adjustment block that I showed earlier. And so I can use this table to edit what's here to make a budget adjustment. And so I'll put my hat on as the BFM, the budget financial manager here, and I'll use pandemic 1 that I've pre-made. And so I'll click on edit. And then these fields were already pre-filled for this demo, but I'll fill in the value field. And so here, the value, we'll hit edit element, we'll put in, say, minus 10,000. So we want to remove 10,000 from year 2020, and then we're going to move that to year 2022. And so we hit save right there. And so now it's reflected here in the table as minus 10,000. And so let's go ahead and add 10,000 to 2022. And so there's 10,000 there to 2022. And so now the BFM has made the adjustment. And so if we look at this table now, we have the values minus 10,000 and 10,000 there. But if we go back over to our sprawl chart really quickly, we'll see that the budget adjustment has now has not been made quite yet. Here, I'll show you in the model. So if we go here, see this budget adjustment column, the minus 10,000 or the 10,000 is not there yet. The budget adjustment table that I showed you, these values should be minus 10,000 and 10,000, but they haven't been updated yet. And so that's what I'll do now. I'll put my hat on as the cost modeler, or systems architect, or whatever it may be, the one who's authoring the SysML here. And then we'll go to budget adjustments. We'll go to MMS and we'll hit validate models. And then what this is doing right here is comparing what's in the model and then what's over here in this web-based platform. And so it's saying here that, oh, these two values, there's a difference. There's a difference between what we have here in the model and what's on the server. And so mine is not working right now, but what you could do is you could click on these things, one of these things, and hit display differences. It takes a long time for it to load up, so we're not going to wait on it, but it basically divides this in half. And on one side, it shows what's in this model, and on the other side, it shows what's on the server. So you know exactly what you're bringing in and what you're changing. Whereas this just tells you what's different. It just highlights what's been changed. And so what we'll do now is we'll highlight both of these things. And since we know we want to bring those in because they've been approved, we can go ahead and say update these elements from the server, from MMS, Model Management Server. And so we can update those things. And so now we see minus 10,000 comes in and the 10,000 comes in there. And because there's a connection between the budget adjustment and the RDT and E portion of the sprawl chart, we can click back over here and see, oh, yes, those changes have been brought in. Awesome. But if you'll notice, the required costs have not changed yet. They're the same as before. And that's because the cost analyst now needs to reevaluate these analysis for these 2 fiscal years. And so that's what we'll do now is we will click on these 2 rows, not 3 rows, these 2 rows. And then all we have to do is, because the parametrics and all the analysis is already set up, we can go here and click on evaluate selected rows. And then it'll run through the mathematical representations that are behind these tables. And if you'll look at these required costs, we'll see these numbers change by 10,000. And so there we go. Fiscal year went from 31,000 to 21,000, and 2022 went from 108,000 to 118,000 there. And so now we have this updated values for our sprawl chart here. But if you'll look back over on our sprawl chart here, we still have 31,000 and 108,000. So now it's up to the cost analysis or the modeler here to re-update those values back on the server end, so that the budget finance manager, when they come back to see the impacts of the changes that they made, they'll be able to see that on the sprawl chart, how that affects the required cost and so on. And so the way that we'll do that here is very similarly to what I showed you before, just right clicking on that MMS, validate the model. And then this will compare the two, see what's different. And then it'll ask us if we want to push these values to the server, or if we don't want to worry about it or anything like that. And so anyway, here we have, it shows us what has changed. And so if we change required costs, then the delta required also changes. And so now we have these 4 things that are different between what's in the model and what's on the server. And so we'll highlight these things, select these things, and then we can see if we didn't want to push these results to the server, then we could say ignore for me or ignore for everyone. And then that way we maintain consistency between what's in the model and what's on the server, and then also have full control over this. And also these types of rights right here, people can be granted permissions and access rights to be able to do these types of things as well. And so what we'll do now is we'll commit these values to MMS so that the budget finance manager is able to see the impacts of those changes. And so now we'll flip over to our RDT&E table here. We'll hit refresh, putting the BFM hat on again. And then seeing, oh, okay, now our required cost because of pandemic adjustment 1 is now 21,000. And this is for fiscal year 2022, it's 118,000. And so now we can observe those changes as well. It's also on here. It's reflected in the budget adjustments as well. They can see that transaction from minus 10,000 to 10,000 there. And so with that, we conclude this demonstration for the budget adjustments, showing the capability of being able to interact with the model without actually having going into the model, because sometimes SysML can look very complicated, and you don't necessarily have to interact with the SysML to see the results of SysML, which is very powerful. And so with that, we'll move into the next demonstration, which involves the P sheets. And so we'll go down here to our P5. And so this shows that we have the P5 sheet from the cost model, and it's done using this cost roll-up pattern. So I'll zoom in a little bit here so that you can see the properties there that we constructed on the cost roll-up pattern. So we have the P5 block, and its parts are all of the parts of the P5 sheet. And so, yeah, flyaway costs, recurring costs and its parts, other flyaway costs and its parts, and then so on and so forth, showing all of the constituent parts of the P5 sheet. And so we use the cost roll-up pattern for this. And that's what this looks like here in the parametric diagram. And so you can see here again, we have these value properties: level cost, unit cost, quantity, unit cost. And these are the same ones here: quantity, unit cost, level cost, and unit cost that you see on the parametric diagram. And so we can relate these values with the subtotal cost roll-up pattern, and then using this sum child of command or function here, so that we can construct this table, create instances for each fiscal year. So we're looking at fiscal year 2033, and then looking at the unit costs for each of these and the quantities. And these are just representative numbers here, and just to show you what it looks like. So if you add up all of these things here, then and you have put a quantity here for recurring cost, then it'll add up to 65. And then you can add this all the way up for the fiscal year and get 216 for all of these parts. And so we're going to look here at the airframe CFE, and we see that the unit cost for that is 12.25. The quantity is 3. So if you multiply that, you get 36.75, and that'll be summed up. All of these children sum up to its parent level here, and then these children get summed up to its parent level, and then all the way up to the fiscal year there. And so that's what we mean by summing the children up to the parent level, and then all the way up to the great grandparent level, I guess. And so I want to demonstrate here with this table how you can sync this with an Excel file. So we've demonstrated how you can sync it with a web-based platform, but also you can sync it with an Excel file. So if someone somewhere wants to interact with the model via Excel, then that is possible. So the values on this table can be manipulated by looking at this Excel sheet. So this is the same table, and it's the same thing, has the same names here. And so if we look at the airframe CFE, we have 12.25 times 3, 36.75. So if we change the quantity here, so say we change it to 4, we hit save, and then we go back over here to the model. It hasn't quite updated yet, but if the modeler will just go read from file, and then we select airframe CFE right here, then that will update the value there. And so that's 4. But we now know that 12.25 times 4 is not 36.75. It's actually, in fact, 49. So we'll have to go and simulate this instance again, just as I showed you before with the RDT&E table. So we'll find this instance in the containment tree. Well, I'll show you what it looks like to simulate an instance with Cameo Simulation Toolkit. And so this loads up the simulation, or loads up the instance in the simulation pane here. And then so you can see all of the values that are on the P5 are now here. So if we go to our flyaway costs, it was recurring costs, and then airframe CFE is the one that we were looking at. Oh, so now it's 12.25 for, oh, there's the 49 that we were looking at. And so now we want to update those values on our P5 table. So in the containment tree, which is very small, let me see if I can, yeah, there we go. Open that P5 table again. You can see it's still 36.75 in the table. So if we'll take this and export to instance button, we'll click on that, that updates that 49, that value to 49. So if we flip back over to the Excel sheet, that still says 36.75. So now we need to update the Excel sheet so that they can see the impacts of those changes. So we'll first you have to close the file because you can't write to an open file. And so we'll write to file, and then we can open that back up again and see there we have the changes. And so in that way you can sync your model with Excel sheet and then and have that flexibility there. And also I tested that you can have this Excel sheet on a server, and it worked. It worked for when I had it on Microsoft Teams, and then opened that up and was able to change things in the Excel file, bring it into the model and show and do exactly what I just showed you there. So the last demonstration here with the time remaining is going to be the cost equation demonstration, substituting cost equations. This thing is in my way. Can I move it? Yes. Okay. So I'm going to switch over here to the equations project usage example here. The cost equations. There we go. Okay. Sorry. The cost equation parametric estimation. So I've showed you this diagram before that shows all of the equations for the SRR1 cost methodology. And so these come from the RAND document. So these are all the same equations. But what happens if you have two sets of equations? Maybe you have a representative sets of equations while you're developing the model, but then, or you don't want people to necessarily see proprietary equations that you want to use later. So we use these representative or surrogate equations is what we'll call them for the time being. And then later you'll want to substitute in the real equations into your parametric calculations here. And so I've created these what are called opaque behaviors, which have scripts in them that manipulate model elements to be able to change what equations are being used in this parametric diagram. And so right now, if we look at one of these, you can look at the type, and it says the SRR1 cost, which are the cost estimating relationships here. And so these are representative of the surrogate equations. And what we want to do is bring in the real equations, which are in a project use, like I talked about earlier, model cost estimating equations. We want to bring in these equations to this. And so what'll happen is when I run the opaque behavior, this will change from SRR1 cost SERs to cost estimating equations, which signifies that we have successfully swapped these equations out, and then can use them to construct a comparison of these equations to see which ones we want to use. So since these are the surrogate equations right now on the constraint blocks, we will go and grab the real equations. So we'll run this opaque behavior. It loads up, we hit the start button here, and it runs through, it goes through, it does it. And then we look at the our constraints here, and we see, oh, now it's not SRR1, it's not the surrogates anymore. It's the one from our cost estimating equations model. Okay, awesome. So now we've got different equations. We can run the analysis again and then compare the two equations. So we can compare the surrogate set of equations and the real set of equations. And so these regressions right here, these numbers are the same because these are inputs. So we kept the inputs the same. And then you can observe the differences of those two sets of equations for each of these metrics down through here. And so just like that, you can switch out the equations using opaque behaviors. But there's also another way to do this. There's another way to switch these equations that don't involve using a script. It's actually using SysML elements called generalizations. And so all of this works by using a state machine. And so we have this Geyser cost model block, which I've showed you many times before, an instance of that. And then we have this program cost estimate constraint, which is this relationship here. And so using this generalization relationship, we're creating a specialization of this program cost estimate. And so this inherits the same properties, so it'll have the same properties, but we can give it a different equation. So if you look, it's very slightly different, 4.3 there and 4.5 here, 2.57 there, 2.87 here. So just the numbers have been changed slightly just to demonstrate what this looks like. And so if we'll switch over to the state machine diagram now, we have these different states, these yellow blocks, and these represent which equation set you're using at the time. So if we're in the specialized equation set, that means we are using this equation, this specialized equation. But if we're in the standard, then that means we're using the original equation here. And so all of these states can be, you can maneuver between these states by using these signals. And so I'll demonstrate what that looks like now. And so we'll right click, we'll go to simulation, and we'll run with context this time. And this will take a minute to load up. And as it loads, I'll explain that we will change these signals. And when we change the signals, it will change the sets of equations that we're using. And so what'll happen is this is actually loading up the entire Skyzer cost model simulation. So when I hit run, you're going to see this run through many behaviors and activities, and that's the ones that are behind the Skyzer cost model or even in the Skyzer system model that we're using. So before I do that, I want us to look down here at program cost and see that it's 283,000. And so we're going to look at that number as we run through the simulation here. And so it's running through all of these behaviors that go through that are involved in the Skyzer cost model and in the Skyzer system model. And so now we can look back at our state machine diagram. So we're still looking at our program cost value here, which is right there, 283,000. And so it's still the same. And so we click on our state machine diagram. And if you'll notice, we're this red diamond here, that's where we are. It's waiting for us to tell which equations to use. And so by default, it uses the standard, but now we can use these triggers, what are these signals to say, okay, we want to use the specialized equation set now. And so then you'll see that this goes to the red box, or the red box highlights the specialized equation set, which means that, hey, we're in this state now. And so if I click back on the Skyzer cost model, we can look at the program cost, and wow, there's a significant difference there. We went from 283,000 to 18,000. And so if we wanted, we were like, oh, wow, that's just not right. We need to go back to the other equations. Then we can just click right there, and we can go back to our standard equation set, and you can see it switches over to this state. And then we can see that the value has now been changed back to that 283,000. And so in that way, you can use these signals and these state machine diagrams along with generalization relationships to switch between equation sets. And then you can create instances of this however you need. So if I were to switch it back and forth, I can create these instances and then create a table much like you see here. And so with that being said, that completes these demonstrations. And now I'll turn it back over to Dr. Mark. Thank you for your attention.
Thank you, Taylor. That was excellent. We used up all of our 2 hours. I did have an accomplishment slide that I was going to put up there, but I think that we'll just open it up and see if there's any more questions. We did get a couple of questions. One about the models. The models are distro D still currently, and they might be, but we're trying to get them to be distro A. There was other things about how one would actually deal with variants, and yet there's a couple ways. One is either create different instance tables or also use branches. There was a couple of questions about, let's see, what was the other question here? Oh, about ONS, why we didn't actually have anything in there for operations and sustainment, because we were only at SRR2 in our simulation here that we went through. I think that might have actually done it. I know that Mimi actually sent all the answers back in the chat anyways.
Yeah, I think on that last question, Mark, I would also add is the this what was done that Mark and his team have done is they kind of proved a structure that we could utilize. Is this a 100% complete model? I would say no, it is not a 100% complete model. The other thing is I just want to clarify. When we talk total ownership cost, okay, that is the cost of development, it is the cost of production, it is the cost of ONS, and the cost of disposal. That is also synonymous with the term life cycle costs. So total ownership costs, life cycle costs are the same thing. Operation and support costs is not equivalent to life cycle costs, and I see that happen all the time where people think life cycle costs is just the ONS piece. No, life cycle is, again, from the beginning, development, production, ONS, and disposal costs. At one point in time, there was going to be a difference between total ownership cost and life cycle cost, and that was to include the indirect costs associated with an individual program. But that proved to be a bridge too far, as they say, in the ability for us to not only estimate but constantly maintain. Over.
Yeah, so I did see one more question. I don't know if we can keep going for a second, Mimi. Is it okay?
Yeah, absolutely.
Okay, yeah. So Jeffrey, it turns out that it's like I hope that was clear that it's like, yes, a change in MMS is not the same as the change in Teamwork Cloud. And the thing is that also there's different authorizations that can be done with people in the MMS. So for example, maybe the BFM, the budget financial manager, might have access to actually make changes and requests in the model management system, but that person may not be, and probably will not be, the same person that would then be able to actually synchronize the MMS to make a decision about committing back to the Teamwork Cloud, which is really going to be the authoritative source. So hopefully that is a more complete explanation. I think that Taylor actually did go through that, but I wanted to make sure I clarified. Okay, with that, it's like, unless there's additional, let's see, what's the last one? Yes, there is published papers on this. The is WRT 1036 on the SERC website actually has descriptions of a lot of this stuff, and actually has more of a comprehensive description of a summary of everything that's going on. We also have a number of artifacts from the All Partners Network, and so therefore there's a distro A place that actually has some things if you actually are a government contractor. There's a research site that has some information that may not really be distro D, government only, but it doesn't necessarily have a marking of distro A. So there are more artifacts, about 60 products, including videos and papers and models on those kinds of things for contractors. So with that,
it wraps us up. We are a little bit over time, but I appreciate all three of you presenting. And again, we'll have the playback available for folks as soon as we exit.
all right. Thank you, Don and Taylor and Mimi.
All right.
And Kunal.
Thank you
for helping us get set up here. Thank you very much.
Right.
Have a great
Right.
day.
All right, bye-bye.